words about groins. So what are groins? And it's very simple. Groins are a coastal defense that is often coupled with breakwaters. Breakwaters basically, they contrast the cross-shore sediment transport. Groins contrast the long-shore sediment transport. Let me show you what is a groin, because, okay, this is a groin. And let me give you another picture, because this is not very clear. Are you? This is clear. Yeah. Basically, they are structures that are perpendicular to the coastline. So breakwaters are parallel, almost parallel to the coastline. Groins are perpendicular. They are not strictly perpendicular. They can be tilted a little bit. They can have an inclination not really perpendicular, but in any case, their direction is cross-shore, while breakwaters are along shore. So you can understand that by crossing the shore, they stop along shore sediment transport, while breakwaters, which we don't discuss, they stop the cross-shore sediment transport. We don't discuss breakwaters because you studied them with Professor Archetti. We are instead focusing on groins. Keep in mind that groins can be spelled in this way, or depending on, American English or I should have here, or like this, with a Y. It's doesn't matter, it's American English, UK English, okay? Okay, now, basically, in their simpler shape, they are just a perpendicular structure, if you have the shoreline here, with an along-shore sediment transport, which is causing erosion, because along-shore sediment transport, you know that can cause erosion or accretion, depending on the energy of waves. When we intervene with a structure, with a defense structure, typically we have erosion due to along-shore sediment transport. So basically the energy of waves takes the sediments and brings them somewhere else. This is something that it is desired, because usually we desire that the sand from the outlet of rivers or from inlets in general is brought away by the current and displaced somewhere else. But then this along-shore sediment transport sometimes can cause excessive erosion, typically by human impact. So there is a human impact, for instance, because the delivery of sediments by rivers is decreased, or other kind of human impacts that alter the equilibrium. What we see generally is the result of a long-term equilibrium. When there is an alteration due to human impact, then the along-shore sediment transport may prevail and erode. And therefore, simply what we do is to build a structure which is displaced like this. In this way, of course, the energy of waves along shore is decreased, and what we cause is sedimentation of sediments. We trap the sediments, we decrease the energy of waves, of the long-shore component of waves, and therefore we trap the sediments. What happens? First of all, as we will see, if this is the shoreline, the groin doesn't stop here. It continues for a while, typically up to the berm. It can be visible, or it can be buried into the sand up to the berm. Or in some cases even the dune, which is even more inland. So what happens if we stop this along-shore sediment transport? What happens is that we have an advance of the shoreline for sedimentation. And typically what happens is this advance is higher in the proximity of the groin and at a distance from the groin. So basically the new shape of, the new shape is something like that. And unfortunately, we have to take it into account, increased erosion on the other side. Increased because, of course, we stop the sediments, there is sedimentation here, and increase the erosion here. But this is the effect that we want to reach, and then, of course, there is an increased erosion, and then, again, accretion. On average, we have an advance of the shoreline, and you can clearly see this kind of shape up there. You see that also for the specific shape of the groin, it is a bit complicated. It's not just a groin that is one straight and perpendicular structure to the shoreline. In this case, there is a bifurcation. You see the head, what is called the head of the groin. It's a bifurcation in order to extend this action of stopping the energy, trapping the energy and the sediments. And therefore, also due to this kind of specific shape of the groin, you get like a circular accretion, a circular shape for the accretion between the groins. And in this case, you can clearly see, understand the effect. Everything you see, the beach that you see up there probably would disappear if you removed the groins. And probably erosion would extend up to the road that you see in the background. By placing the groins, they trap the sediments and build the beach. The first thing to consider is that you have to use groins when you have a long-shore sediment transport. They are not effective in cross-shore sediment transport. They may even exaggerate the cross-shore sediment transport. Why is that? Because, of course, if they trap the waves between the groins, the movement of the waves becomes amplified in the cross-shore direction, and therefore they may even increase the cross-shore sediment transport. This is why very often you see groins coupled with breakwaters. So they have to be used carefully when you suspect that there is cross-shore sediment transport. They are effective for a long shore or long shore. Yeah?
Do we use modeling also to simulate how we...
Yes, but let me introduce the topic before, okay? Because of course we need to model it. Yeah, but let me introduce it. Okay, so our problem is how to design them. And basically we can get a perception of how they work, but we need to get an indication of how to design them. Like many other issues related to coastal engineering, usually the design is done through empirical approaches, because in order to get a physical modeling of the action of groins, this is complicated. And we already saw a model, the one-line model, that can be used to study the morphology of beaches, that can be adapted, and we will see how we could adapt it to represent the situation. If we put a groin and assume that the groin is a fixed point along the beach, you can modify the model that we already applied by putting fixed points, and you will see that the model correctly simulates the position against the fixed point, and increased erosion, downdrift. But this physical modeling relies on very heavy assumptions and needs to be preceded by an empirical investigation of what happens. So we will focus on empirical approaches for estimating groins, and then I will provide some details on physical modeling. Okay. Now, some classification about of these structures. They can be classified long or short. Long are depending on how far across the surf zone they are extended. A groin is classified long when it is extended to cover all the surf zone. The surf zone, I remind you, it extends from the breaker line of the waves. Did I start the camera? I don't remember. Yes. And from the surf zone, I was saying, is extended from the breaker line of the waves up to the swash zone. The swash zone is the zone that is covered by the wave run-up, the wave up and down. Okay? The surf zone is where people surf, of course, and it is from the breaker line to the start again of the swash zone. The surf zone is seasonal, so this definition of long or short groin is ambiguous, it's not unique. A groin may be long in the dry season, let's say, in the summer, in the quiet sea season, and can be short during storms. But in general, our definition of long short makes reference to the extension of the surf zone. And typically groins are realized to cover all the surf zone, at least the surf zone during the summer season. And high or low groins, what does it mean? Some groins may be partially submerged, and therefore they are called low groins. If they always emerge, they are called high groins. Even in this case, you may have groins that are submerged by only heavy storms, and therefore the classification may be ambiguous. But usually, when we speak about high groins, where they are higher than the high tide level. So we get the highest tide, and if the groin is significantly higher, like at least 1 meter higher, we say that it's a high groin. So basically, we make reference to an average situation, okay, to say that it's high or low. Okay, and let me see if there is something that, okay, another important thing, permeability. Groins may be impermeable or permeable, depending on whether or not sediments can pass through them. A permeable groin usually has apertures, so it's not a compact structure. Compact structure is made by boulders. If you made a groin like you make a breakwater, so with boulders, this is possible, it's considered not permeable. Even if, of course, some permeability exists, but for sediments it's very limited. Instead, if you take a groin like this one, because sometimes they are made by woody elements, here. This is permeable. I'm not sure if you can see it, probably not, but this is permeable because water can pass from one side to the other side, but still they break the waves. They slow down the energy, they dissipate energy, and therefore they favor the position. But of course, sediments can bypass them to some extent. And in some cases, this is a desirable feature because, you know, a groin is very impacting. If it is impermeable, it stops sediments and can cause erosion downdrift, and therefore we may be concerned by this. Okay, let me see the permeability. Okay, I think we already discussed this. Okay, leading parameters for the design. So, let's see. We need to understand wave behaviors. In order to design, we need to know the wave forcing, and we need to know if there is a longshore sediment transport. Sometimes I use longshore or alongshore. I think they are both correct. I need to check anyway because I'm not sure. Yeah, you have a question. Okay. It's important that we understand each other. So alongshore, let me say, alongshore is clearer. And also we have to design the groin length and height. And keep in mind that another leading parameter is leading parameters of what? Sorry, not for the design. Leading parameters for the final configuration of the beach. So what determines this final red line shape? Wave behavior, growing length, C depth at the tip of the groin. Tip is the head of the groin. It's here. Okay. And groin length. Length is the dimension of the groin in the cross-shore direction versus their spacing, distance between groins in the long-shore direction. Okay, so let's try to understand from a qualitative point of view what happens. First, the shoreline, if the groin is straight, rarely reaches the end of the groin. Why is this? Because there is bypass of sediments at the end of the groin. What is bypass? Bypass of sediments. This is permeability. Permeability favors the movement of sediments through the groin. This is bypass. So basically, when sediments get trapped here, they basically settle down up to a certain extent, but when we get closer to the end of the groin, there is still some energy here and sediment bypass. So this is the reason why usually the new shoreline doesn't reach the head of the groin. If we want the new shoreline to reach the head of the groin, what we do is to use a T-shaped one. Like the one that I showed you before, if you remember this one. This is a kind of T-shaped. Why they used this bifurcation? Because they wanted to get the shoreline close to the end of the groin. Of course, if you use a T here, what happens is that energy doesn't bypass, the waves don't bypass the groin because they get trapped here. And therefore you have that the shoreline may get to here, up to here. Okay.
Then we don't have diffraction.
Yeah, you have diffraction. And also this is due to diffraction, correct. This is also due to diffraction because when you have the wave that approach the groin frontally, and basically they turn around for diffraction and therefore they remove some of the sediments. And so this is also due to diffraction, yes.
But why in the arbor we don't have this shape? It's not better to have the T shape?
In the arbors?
Yeah.
Because, you know, sometimes they are used in the arbors. When you want to protect the arbor from the long-shore sediment transport, they also use the T-shape. I think that, you know, the reason for using the T-shape is to make the effect of the groin heavier. So if you want to better trap the sediments, like for instance, sometimes you have the arbor here. Here you have an arbor. And what you do is that you make a protection like this. Because this is because you want to stop the long-shore sediment transport in this direction. And you can see this kind of protection in the arbors. And usually, sometimes they are done in this way in order to have more room, to gain room for putting boats there with the, you know, to park the boats. But it is also used the shape in order to trap the sediments. I'm not sure if I replied to your question.
No,
It's okay. Okay, so bypassing and permeability, I already mentioned them, what it means. So keep in mind that groins can be bypassed and sediments can move through them if they are permeable. And this is a feature that is to be considered. And look, again, permeability is a desired feature in order to avoid accumulation of large volume of sediments. Because, you know, if you want to make an intervention that is gradual. The best thing is to first put in place a permeable groin, maybe with large apertures, in order to make your intervention less impacting. And then you see what happens, because when dealing with the sea phenomena, experimentation in a real scale, so real experimentation is the best thing to do. So you first use an intervention that is less impacting, you see the results, and then if needed you reduce the permeability. And this can be done also on the fly by modifying the groin that you have built in a first instance. Sorry. Okay, so this is what we need to design. The length of the groin, the spacing between groins, spacing and length are the main parameters. Elevation, porosity, which has an influence on permeability. Tapering is basically, groin can be done in this way. And this is a tapered groin, a tapered form, meaning that the groin is larger toward the sea and the width is reduced, getting close to the shoreline. This is an alternative. It's an alternative with respect to the T shape, and this may be less impacting from a visual point of view, because also the visual is important. We will talk about the visual in the continuation of this lecture. The angle with respect to the shoreline, we will see how to determine it, and the shape, straight, angled, T-head, spurred. Spurred means with spurs, okay, like this one. This one can be defined as a spurred groin. You know what is a spur? Okay, the spur, it's written spur. It's something like, let's suppose that this is a groin, and these are the spurs. The spurs in Italian are called speroni, and they are used, you know, the horse, when you want to stimulate an horse, they put spurs in the shoes, and you understand? Okay. Sperone means spur, and the most used, if you look at the dictionary for spur, they talk about horse, how to say cavaliere, horse?
Nine.
Sorry?
Nine.
Ah, yeah, knight. The knight, but knight I think is more in a army meaning. I think that military is knight, but the horse driver, how is it called in English?
Horse rider.
Horse rider, okay. Horse riders have the spurs in the shoes. Okay. Horse rider. I think horse rider is
Someone with a spear.
Yeah, knight, not the knight.
yeah, knight is more military, or no?
No, it's a knight. You don't pronounce the cake.
Okay,
Yeah.
knight.
Yeah,
Okay,
knight.
but it's more military.
Yeah, it's yeah, or the horse side.
Okay. Anyway, I think we understood what is a spear, okay? Okay, so these are the things that we have to design. Sorry, let me go back to the presentation. Okay, now, first we have to analyze beach parameters, because if we want to pass to design, there are a series of parameters that we need to define. So the groin parameters, I go back, the groin parameters are our design variables. And the beach parameters are our drivers. We need to know these beach parameters in order to perform our design of groin parameters. So we need to know the depth, the sea depth at the tip of the groin. So basically we need to know the beach slope. This is extremely important and relatively easy to understand, to detect, to survey. Beach morphology, slope of the beach again, berm height, shape of the shoreline, etc. Depth at the average breaker line or beach closure. This is another important issue, which is basically average breaker line is basically the location of the tip of the groin in most of the cases, but not in all of the cases. Sediment transport, sediment availability means characteristics of longshore sediment transport, grain size and variability sediment density. These are the parameters that we need to try to understand, because if we want to apply a physical model, we need to know these parameters. Empirical rules sometimes neglect some of them, as we will see, because we will start from a very simple rule that doesn't need the knowledge of these parameters, but for a detailed investigation you need to know that. And then the wave forcing, and this is what you already know also, wind and wave behaviors. So height, period, direction, also because they allow you to compute a longshore sediment transport. Wave direction is extremely important because, as we will see, we need to orient the groins in a way that they are approached by waves on average perpendicularly, meaning that if I have this kind of shoreline and on average waves approach the shoreline along this direction, which is of course concerning because it causes a longshore sediment transport, we have to place groins so that they are almost parallel to the wave direction. So they are not always perpendicular, as I said, but basically what we need to do is that they are placed almost parallel to wave direction. Okay, this is extremely important. So, rule of thumb. We start with some empirical rules, or rule of thumb, in order to understand the basic behaviors of groins. And then, if needed, we apply a physical model. This is the approach that we follow here. And when we talk about rules of thumb in the design of groin, there is one golden rule that is used worldwide, which is called the 1/3 rule, or the lambda shoreline rule. So let's try to understand what is this rule. It is very simple and very rough in a way, but it allows us to understand how the groin works. And basically, what does it say? If you look at the figure, if you look at the groins, and let's forget about the T-shape for now, let's look at the straight groin. Basically, if we indicate with the low water shoreline the upper blue line, and with the high water shoreline the lower blue, which means that when you have low water, you have the shoreline that advances in the offshore direction, of course. And let's indicate with W the distance between these two shorelines. Basically, the lambda rule says that the new low water shoreline, the upper blue line, settles at a distance lambda g from the head of the groin. Look at the straight groin. You see that there is a distance lambda g from the low water shoreline to the head of the groin. G is the distance between groins, groins interspace. Lambda is usually taken as 1/3. So this is the 1/3 rule. Basically it says, okay, you put groins on the pre-project coastline. with a given direction. We will see what is, I already gave an anticipation. And then we measure the distance of the new low water shoreline from the head of the groin, as lambda g, where lambda is 1/3. This is the 1/3 rule. There are some assumptions in it which we will see, or more than, instead of assumptions, conditions. A more precautionary design would be obtained if we set lambda to 2/3. So, this is an implication of the rule. Like, if you want to be safe, take lambda 2/3. Okay, now let's focus on the T-shaped groin. First, lambda, you see, it's measured lambda g from the extreme of the T, which means that you get a shape of the new shoreline that is carved in the proximity of the groin. And therefore, what is the effect of the T? The effect of the T is to bring the new shoreline closer to the head. And the more the width of the T, the closer the shoreline to the head, because you measure lambda g from the extreme of the head to the groin. And therefore you obtain a carved structure. And this is what you can see here. Again, I go back. Why they used these spurs? In order to bring the beach, to extend more the beach in the offshore direction. And this is explained by this lambda rule. Actually, a kind of carved shape is obtained also for the straight groin, because, as we said, there is diffraction, there is accumulation of sediments, and therefore the shape of the shoreline is not straight of the new one. Even if we use a straight groin, non-T groins, non-T-shaped groins, we don't obtain a straight line. There is always some, some curvilinear shape close to the groin. But if we want to increase this effect, if we want to bring the shoreline closer to the head, we have to use the T shape. And look at the distance, I come to you, distance G, where it's measured, from the extreme of the T. Question?
I didn't understand how we can define the LWS and HWS.
Okay, basically the LWS is the new shoreline with low water, which low water means low tide and summer season. And high water means high tide. And of course, when you have a rising water, because it's high water, you get the shoreline closer to the land. Is it clear? And then, depending on you can define the elevation difference by looking at low tide and high tide. And even if you don't have tides, like if you look at the Adriatic Sea, the tide is minimal, but still you have a shoreline in the summer season and a shoreline in the winter because of increased storminess in the sea. And therefore, you can define what is the average water level in summer and winter. And you see the elevation difference. Depending on the slope of the beach, you compute the difference in the horizontal direction over the map.
So before designing these, we have to, it is a design criteria, we say we want our new coastline to be this high or this low?
Yes, basically we make reference, we have to define, first of all, in the pre-project coastline, why don't you see any difference? Because usually the slope of the beach becomes, in the pre-project coastline, is higher. After your project, you have a more gentle slope, and therefore, basically, you have an increase. You have a difference between high water and low water shoreline, which is may be not there in the pre-project case. So basically you have to decide in your project where do you want the new shoreline during summer and during winter. And then basically the lambda rule of thumb refers to the low water shoreline. And then there is a difference W that you can estimate depending on the tidal areas and the areas of the beach.
And then capital G, how do we get it?
Capital G is to be designed. Basically, let's suppose that it's the distance between groins, and therefore, if you increase the distance, you retreat the shoreline. So it depends on the shape of the new shoreline that you want. You have two options, two possible options. If you want to bring the shoreline forward, you can increase the length of the groins by taking into account that if you go beyond the breaker line, the effect of groins is less significant, or you can make them less spaced. You increase the frequency, basically. So this is a design variable, and we will discuss it later. So basically, your first question is, okay, let's suppose that I want to bring the new shoreline, low water shoreline, to that level. So your design variables are the length of the groin and G, and they are related to each other. So of course, if you make more groins, they can be shorter, they can be short groins, and you make many of them. If you want to get them very spaced, then you have to increase the length, but not going beyond the breaker line. Is it clear? Okay, perfect. Okay, this is our rule of thumb. And now, you can increase your lambda value, and they are more appropriate for energetic environments. So if you have very energetic environments, of course, you have more erosion, and therefore the groins are less effective. And also, it's safer to increase the lambda value if you have uncertainty in the definition of your design variables, in the definition of the wave direction, etc. And